Let us begin with the practice assignment sessions for the course contents covered in week 9. Since we are nearing the end of the session, so what I thought is for 5 minutes or 5 to 10 minutes per session, we'll have a brief overview of one set of lectures. Say today we'll be covering the brief overview of lectures from 1 to 19, for the next session 19 to 30 and so on. So I'm just starting on with very brief overview of the topics covered in each lecture to just get the flow or to just brush up on the topics, whatever you've been seeing in the course. So can we begin? Okay. So when you guys started with the course from lectures 1 to 4, you had the overview of cellular systems in general. You calculated what is the data rate, what is the battery life, how do you find the battery consumption or how much battery that is left. So those were the calculations part. And then you saw the transmit and receive chains in the transmit side, like what are the different blocks present in the transmit chain, like from the information source, error correction coding, and then the modulation and so on. In a similar fashion, the receive chain, and then wireless channel. So what are the different um, topics that will come when we think about the channel? So first thing will be multipath. Second thing is Doppler. Whenever there's velocity, there's a Doppler that's associated with it. And because of multipath, you'll be having time dispersion. And then you saw about co-channel interference, then adjacent channel interference, and then the way to calculate the link budget, receiver sensitivity, and then adaptive modulation, that is based on the SNR. If you have a better SNR, then you could go for higher considerations and so on. And then multiple access schemes like FDMA, frequency division multiplexes, time division multiplexes, code division multiplexes, and then an overview of OFDM. And then about establishing a call and various other aspects of 4G, 5G, and other wireless technologies. So, in brief, you had a discussion about all the topics in these 4 lectures. And moving on in detail, generally, what is called as a downlink. So, from the tower to the base, from the base station to the mobile, you call it as a downlink, and then goes the reverse link from the mobile to the tower. It becomes an uplink. And then when you have a base station and a mobile station, you can either transmit through a frequency division multiplex or a frequency division duplex or time division duplex. So in frequency means they will be transmitting, the downlink and uplink will be in different frequencies. In time means they'll be in different time slots. And then when do you need a duplex filter? And then about different multiple access schemes, that is when multiple users want to transmit simultaneously, then multiple access schemes come into picture. So this were the different topics in lecture 5. Following on, then you saw about path loss. So in free space, what will be the power received? So it will be the transmit power scaled by or attenuated by a path loss, which is based on the distance. So PR will be PT divided by 4 pi d by lambda the whole square. In dB, if you have to write, PR will be PT in dB minus the path loss in dB. So this term 4 pi d by lambda the whole square is called as the free space path loss term. So you saw about all these things. And then in general, the gain of a parabolic antenna and these things, and the breakpoint model. So what you define, why did the breakpoint model come into existence is like when you have a situation wherein up to some distance you take the path loss exponent as n is equal to 2, and after that when you want to consider a path loss wherein n is greater than 2, path loss exponent n greater than 2, then comes the breakpoint model. So these were the different things considering the path loss. Then the basic idea behind link budget. So when we have a transmit power, So you boost the transmit power by an antenna gain, and then you have a cabling loss that comes. And so whatever you get after all these three things, summing up of transmit power and antenna minus cabling loss, is the effective isotropic radiated power. Then comes the path loss because of the distance, and again it will be boosted by a receiver antenna gain, and then you have the noise figure, so it still reduces your power. Above the thermal noise floor, you set up a minimum SNR that's required. So this is the part about link budget. And when you have a okay, then noise floor. So the thermal noise floor depends upon K, T, B and F. So K is our Boltzmann constant, T is the temperature, it will be in Kelvin, B is the bandwidth in Hertz, and F will be the noise figure of the at the receiver. And when you have a cascaded system, the noise figure for the overall system will be F1 plus F2 minus 1 by G1 plus F3 minus 1 by G1, G2 and so on. So it's like the major terms will be the noise figure and gain of the first stage. So generally what they say is, for the first stage, if we are able to identify F1 and G1, then it will be really helpful to lessen the impact of the further stages also. So that is F overall. And a noise limited system and an interference limited system. So when we consider a noise limited system, what do you say, the main factor will be noise. So how do you see is, when you have a particular minimum SNR required for transmission, so if this is a received power level, so up to this point we could still be able to get some signal which is above the minimum SNR that's required. So up to this distance we could still have a good transmission. But in an interference limited system, the limitation will not be based on SNR, but it should be based on SINR. And the next concepts were cellular concepts about frequency reuse, cell planning, and then about hexagonal geometry. Why hexagonal geometry is a better option than the circular ones and square ones. And why should we go for another coordinate system, a UV coordinate system? And in UV coordinate system, how do you find the distance, actual distance between 2 points if it's given in UV coordinate? So it will be u1 minus u to the whole square plus v1 minus v2 to the whole square plus u1 minus u2 into v1 minus v2. The square root of this multiplied by r into root 3. So this will be the actual distance between those 2 points. And we saw what will be the valid cluster size. So it will be I square plus j square plus ij. These will be the valid cluster sizes, and the main parameter will be d by r, which will be root of 3n. And about the carrier to interference ratio, so it will be power of the signal divided by sum of powers of the interferers. And the upper bound, or like approximately, it could be written as 1 by I naught, where I naught is the number of interferers, into d by r the whole power n. That is, power of the signal will be directly proportional to r power minus n, and the power of the interferers will be directly proportional to d power minus n. So it's r by d the whole power minus n. So here it will be d by r the whole power n. And if like the impact of n on Ci, all these things are had covered. And the difference between like a good RSSI and the actual receive signal quality, that was also discussed. So even if we have high RSSI, if you have a poor receive quality, then it means that the channel is not good, and then you should definitely have an intra-cell handoff, because this will be majorly because of noise. Now if we have a low RSSI and a low receive signal quality, it means that you have the channel itself bad. Then you'll have to have an inter-cell handoff. And then the last case of low RSSI and high receive quality is not possible. And about trunking, so basically what are the advantages of keeping or pooling all the channels together, like keeping them in a common pool? So that was discussed, and the probability of blocking was following like the Erlang distribution, and how MMC like it's like memoryless arrival. We don't know we don't have memory of the calls arrival. So memoryless arrival, memoryless holding time, and we have a finite number of channels. So C channels and C simultaneous users. So that is this M bar C bar C formulation, and the total traffic was given as like total number of users into the average number of calls into average call duration. And in handoff you had so hard handoff and soft handoff, and what are they and all those things. And in further lectures you had the statistical characterization of your channel. So when you have a path loss, it is equal to a mean path loss plus a normal random variable. So basically it was following a log normal distribution, a kind of a thing. And with this formulation, we found the probability of outage. Probability when this x sigma will be greater than the mean path loss minus minimum. So that kind of formulation was also there. And further about large scale fading and small scale fading. So what constitutes large scale fading? The main path loss and the shadowing effects. In small scale fading, mostly it will be multi-path fading. And our channel will basically be a function of delay and time. So even at a particular time, you'll have multiple delay taps. So that is the kind of channel representation we have. And when we have a signal, received signal R of t, it will be Z of t into S of t plus eta of t. And we saw that Z is a random variable. It's a complex Gaussian random variable. So mod Z could be a Rayleigh random variable. And the derivations of all the joint PDF, marginal PDFs. Yeah. So this is like one set of lectures. I know it's quite a fast overview, but the main focus of the weekly sessions is the problem solving part. So I would like to concentrate on that more. So can we begin the problems for today's session? Okay. Am I audible? Yeah. Okay. Consider a system with one transmit antenna and L receive antennas. Independent noise distribution corrupts the signal at each of the receive antennas. The signal has a transmit power constraint of P, and suppose the channel is constant. Yeah, is constant. If L received signals are added to obtain a composite signal, what is the normalized capacity of the channel? So we're adding all the L received signals.
Here, signal power also gets added, noise also gets added.
Mm. Yes.
Both gets added. The net effect change. That's what I see. Intuitively, I feel it remains the same as V by N0.
But we should be having an advantage because
Yeah.
of the L receive antennas.
Yes. 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 Yes.
Mm.
It doesn't a random noise. So signal power gets added. So I feel LP by LC.
Okay. So, if we see the received signal at the kth receive antenna, it's x plus nk. It's the same thing for all the receive antennas from 1 to L. Now we are trying to add all the received signals. So we get Lx plus summation k is equal to 1 to L nk. If we see the power of the transmit signal, it's actually L square into P. If we see the noise variance, it's only L into N naught. So the capacity we can like if we write it as like signal power by noise power, it will be log to the base 2 of 1 plus L square P by L N naught. So we'll get LP by N naught. Say true or false. Frequency hopping spread spectrum has a considerably wider bandwidth.
Spread spectrum by its definition itself is a wider bandwidth and frequency hopping. No, I don't think so. I don't know. Because by the definition of spread spectrum itself, it is spreading on a wider bandwidth. Frequency hopping, shifting frequency, does it increase the wider bandwidth? I think it is false. I don't know.
Any other answer is? Okay. So the answer is false. In frequency hopping, we make a narrowband signal jump in random narrow bands within a larger bandwidth. So basically, if we see the signal at any point of time, it's only a narrowband signal that is being jumped in random narrowbands. But the direct sequence spread spectrum actually needs a larger bandwidth for transmission. So they generally say that the direct sequence spread spectrum is more wider bandwidth than frequency hopping spread spectrum. So in that case of a comparison, this answer is false. Consider the following image. It shows the curves for capacity with full channel inversion, capacity with truncated channel inversion, optimal power allocation, and AWGN capacity. Which of the given curves is most likely to be the one for capacity with full channel inversion?
Madam, can you briefly give understanding of what is channel inversion? I think I forgot.
Okay, so channel inversion means when you have a poor channel, you try to give in more power, something like that. So that you try to keep the channel almost constant. When you have a good channel, you just try to give lesser power. So if you see P gamma I by P gamma, it will be sigma by gamma, where sigma is some constant. This will be for full channel inversion. For truncated channel inversion, it means you won't do this kind of a thing for a bad channel. That is, you omit bad channels and you do channel conversion only for considerably good channels. Say only for channels whose gamma is greater than or equal to gamma naught. So something like that is for truncated channel.
It could be B.
Okay. B or D?
B.
B. Yes. So you're right. The answer is B. In a similar lines, which of them will be capacity with truncated channel inversion? So when you do channel inversion for channels whose gamma is greater than or equal to gamma naught, it is actually much better than the one with complete or full channel inversion. So the answer is C. If in that case, what is the one for capacity of AWG channel? Is it A or D? Yeah.
Yeah,
Yeah.
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 So generally it goes like this. First, the capacity in AWG channel, then the one with optimum power allocation, then with truncated channel inversion, and then with full channel inversion. Okay. Consider a single tap channel of 20 kHz bandwidth with the following SNR statistics or characteristics. Find the ergodic capacity of the channel. So, how do you find the ergodic capacity of the channel?
It will be expectation of capacities.
Okay. So, basically, it will be capacity at gamma 1 into probability of gamma 1. So, um, if you calculate in that sense, the answer will be 61.96 kilobits per second. For a similar situation, find the optimal power allocation for each SNR state of the channel distribution. So, how do you approach this problem? Right. First, what we'll have to do is we know that P of gamma I by P bar is 1 by gamma naught minus 1 by gamma I. So we know the power constraint. So the sum of all these should be 1. So what we do is we first take all the 3 gamma i's and then find what is gamma naught. In that situation, gamma naught comes out as 0.417. If it is 0.417, then it means that this gamma 1, this basically this like gamma 1 is lesser than gamma naught. So it means that we need not even use this channel. Then the second step what we do is we take only the good channels, gamma 2 and gamma 3, and we find gamma naught again. So this will be the best gamma naught. And with this gamma naught, you go back and then you calculate the power allocation. So 1 by gamma naught minus 1 by gamma I. And we know that if gamma I is lesser than gamma naught, directly you take the power allocated as 0. So for the first one, you take it as 0 because gamma 1 is actually lesser than gamma naught. For the other two, you calculate what is the power allocation. You get is 1.218 and 1.218 and 1.28. Is the idea okay? Moving on to the next question. Now you got the optimal power allocation. Now how do you find the maximum capacity? Okay, so the idea will be like as follows. So we found what was P gamma I by P. So it's basically 1 by gamma naught minus 1 by gamma I, and we know the values for it as well. So if you put So if you put 1 plus 1 by gamma naught minus 1 by gamma I into gamma I, you could write it as gamma I by gamma naught. So directly you get to this expression B into summation of we've eliminated the bad channel. So we have only the channels 2 and 3 because the optimal power allocation for the first channel was 0. So B into summation I is equal to 2 to 3 P of gamma I into log to the base 2 of gamma I by gamma naught. So if you calculate this, you get the answer. So this is how you have to find the maximum capacity. In a similar lines, how do you find the capacity with outage? That is, you don't have CSIT. So how do you find the capacity with outage? So what we usually do is you take all the cases. First, we don't have outage. So allowing no outage, we have to send, assuming the channel is always gamma 1. Initially, we think that it is only gamma 1. Now, if you find the capacity, it's 4.03 kilobits per second. Second is, we have outage and the gain is always gamma lesser than 9. So that will be the second case. If we take gamma lesser than 9, then the outage capacity will be 1 minus probability of outage into the capacity without outage. So with this gamma 9, so it is 1 minus 0.2. Probability of gamma 1 is 0.2. So 1 minus 0.2 into this 20 into log to the base 2 of 1 plus 9. So we get 53.15 kilobits per second. Case 3 will be, we have outage, but now the channel gain gamma we take to be 90, like greater than 90. So lesser than 90. So whenever the channel gain is lesser than 90. Now we have probability of outage as 1 minus 0.2 minus 0.4 into 20 log to the base 2 of 1 plus 19, so which is 34.58 kilobits per second. So what we see is the best that could be achieved is in case 2. It's not in case 3, which is 53.15 kilobits per second. This is the trade-off, like this is that balance what we have to find based on which channels to take and which will give the best capacity. How do you find the capacity when channel inversion is performed? So, what is this situation? So, when channel inversion is performed, we know that capacity is B into log to the base 2 of 1 plus sigma, and sigma turned out to be 1 by expectation of gamma. So, directly you could just treat it like AWGN scenario with sigma as the SNR. So now this 1 by expectation of 1 by gamma will be summation P of gamma into 1 by gamma I. So for each gamma I you find out this and then sum it up. So the capacity here, so basically this sigma was found as 0.715 and the capacity will be B into log to the base 2 of 1 plus K. So you get the answer to be 15.56 kilobits per second. In a similar way, what is the truncated channel inversion capacity? So truncated, to find the truncated channel inversion capacity, first what we saw when we considered all the channels, we got sigma as 0.715 and the capacity to be 15.56. Now we saw that for truncated channel inversion, we'll consider only good channels, like we will eliminate the bad channels. So sigma now we are finding with only the second and the third channel. So now sigma comes out to be 15.27 and the capacity comes out to be 64.39 kilobits per second. However, if we consider, because see the best channel is generally a relative term, like good channels is basically a relative term. So if we consider the best channel corresponding to sigma 3 equal to 19, then our gamma 3 equal to 19, then sigma is 47.5 and the capacity turned out to be 44.8. So if you see the best what we can obtain is with by considering two channels and the best capacity is 64.39 kilobits per second. So this is how you will have to approach this problem. Moving on. Which of the following statements are true? Statement 1. The water filling strategy is more power efficient than channel inversion. Statement 2. Water filling is suited to channels that experience fast fading. What do you think about the two statements?
One is true, two is false.
Okay. Actually, the claim is like both are true.
Oh,
One is true for sure because you you transmit data or you allocate power only to good channels. So one is true, so it's more power efficient. Two is true in the sense what we do, even though the channel is fast, we consider instantaneously we consider like this SNR occurs with what probability, this SNR occurs with what probability, and then we are trying to get an optimal power allocation. So water filling is suited to channels that experience fast fading also. But if you see channel inversion is difficult to do when we have a like a fast, rapidly varying channel. You have to allocate power efficiently for a fast fading, frequency selective channel to maximize throughput. Now it's fast fading and it's a frequency selective channel also. I'm sorry. Which of the following will you choose?
both A and B. Uh,
Yeah. So it's fast fading. So we have the instantaneous SNR that's changing very rapidly, which means we'll have to do water filling over time. However, it's frequency selective also. So for every frequency, we have a different attenuation. So we have to do water filling over frequency also. So we'll have to do both. Choose like water filling over time and then water filling over frequency also. In CDMA, multiple users can occupy the same frequency bands at the same time. True or false?
yeah, it is true. True.
Right. So the users will be differentiated based on the codes. So that is CDMA. Which of the following are spread spectrum technologies?
It's like all of the above. WCDMA, CDMA 2000. I don't know
Yeah.
about ES95.
So it's like IS95 was there in 2G standards. Then came CDMA 2000. Then WCDMA is also spread spectrum technology. These are the different spectrum technologies and different standards. Okay. Spread spectrum communication uses chips for transmission and reception of signals. We have a modulator whose chip duration is 1 microsecond, and you're transmitting a signal with a symbol rate of 62.5 kilobaud. What is the spreading factor?
Seems we have to divide the symbol rate with the chip duration.
So if it is 62.5 kilowatt, what will be
Yeah,
symbol
the
duration?
symbol rate is 62.5 kilosymbols per second, and the symbol is chip duration is 1 microsecond. So yeah, so you calculate the symbol duration from 62.5. You can calculate, and then chip duration we know, and that ratio is the spreading factor.
Right.
This is what my intuitive
Yes.
is.
So symbol duration is in microseconds. If we see, it is 16 microseconds. So spreading factor is symbol duration by chip duration. So 16 by 1. So